What is up, everyone? Today we're going to review a paper titled An Experimental and Theoretical Investigation of HCN Production in the Hadean Earth Atmosphere. The title is so concise and explanatory of what's actually in the study, and that's exactly why I love it. But as the title suggests, this work was focused on understanding the production of hydrogen cyanide in experiments that simulated the early Earth atmosphere. A few different things to unpack here for the background, starting with what is HCN? HCN is hydrogen cyanide, which is a poisonous compound, but it is also a key biomolecule precursor, meaning that it can be used with other organic molecules in chemical reactions to form biological molecules like amino acids and nucleic acids that life uses on Earth today. Its importance as a precursor molecule makes it an important one to study in lab experiments and space exploration missions. As for the Hadean Earth atmosphere, the Hadean era was a period of time in Earth's history when we believe the oceans originated and life gradually arose on the early Earth. During the Hadean, the Earth was constantly being bombarded by asteroids and comets, and the atmosphere at this time was very different from what we have on the Earth today. At first, it was primarily hydrogen dominated, which was supplied by hydrogen outgassing events due to the oxidation of iron by water on the surface. And with time, the hydrogen in the upper atmosphere started escaping away, which was then replaced by the nitrogen and carbon dioxide outgassing by volcanoes. In general, reduced carbon, meaning carbon that is bonded to less electronegative atoms, something like hydrogen, so imagine a methane molecule or CH4. This is required as a precursor to produce atmospheric hydrogen cyanide. Whereas on the opposite end of things, oxidized carbon, meaning carbon that is bonded to more electronegative atoms such as oxygen, imagine a carbon dioxide molecule, CO2, is something that inhibits and is unfavorable to the production of hydrogen cyanide. Methane or CH4 is typically the dominant source of reduced carbon in planetary atmospheres, and several photochemical models in the past have found the link between hydrogen cyanide production and methane abundance. But the relation between the two species has never been calculated before, and that's exactly what this study focuses on. The team here came up with a novel approach by combining lab experiments with chemical kinetic simulations, which has many different advantages, starting with experiments simply validate theories, and theoretical simulations help with estimating hydrogen cyanide concentrations produced in those experiments without having to typically deal with pure hydrogen cyanide gas, which I've mentioned before is a toxic substance. Theoretical simulations can also uncover certain reactions which are responsible for the production of hydrogen cyanide. Of course, I'm not going to head into details of the experimental setup and the methods because the goal of my videos is to communicate scientific discoveries and how they apply in the context of the early Earth and how we can apply those models outside of Earth in space exploration and finding life outside of Earth. So rather than delving into the specificities of how the experimental setup and simulations were set up, I am only going to be focusing more on the results and how they're going to apply to other worlds in our solar system. So if you are interested in reading more about the experimental setup and the theoretical exploration, I've linked the study in my description. Go check it out. Heading into the results. This study, like I've mentioned, was the first to find a relation between the atmospheric methane abundance and hydrogen cyanide production at the earliest habitable stages of the early Earth during the Hadean era. Their deduced relationship aligns well with some past experiments, and they noticed a few different things. Of course, this is a mathematical relation, but I know the numbers are not going to mean anything to any of us, which is why I'm only going to be highlighting the important things. Longer exposure to UV or plasma results in a higher hydrogen cyanide yield, which means that back in the day, when there were UV photons coming from solar radiation, they could have acted as the discharge where they would have favored the production of hydrogen cyanide in a reduced atmosphere or in a reducing atmosphere where reduced carbon was more readily available. Hydrogen cyanide produced in the upper Hadean atmosphere trickles down, and that means that it can also carry down as rain to the surface in the environments where liquid water was available with other organics as well, where certain chemical reactions could have taken place to form the biomolecules that led to the emergence of life on the early Earth. They also found that water has a slight impact on hydrogen cyanide production, where an addition of water reduces yield which could be due to ion-based interactions that we just don't fully understand yet, and that's not something that they explored in this study. From their theoretical part of the study, they narrowed down a few different reactions that directly source hydrogen cyanide, and I can certainly go into those specific reactions since I have a background in chemistry, but I don't want to bore everyone, so if you are interested in that, let me know in the comments below, and I'll be sure to make a video on that. Now we get to my favorite part, which is talking about the results and putting it in context of other worlds in our solar system. Hydrogen cyanide has been identified in Titan's atmosphere before, and also in the plumes of Enceladus, both moons classified as ocean worlds where liquid water exists underneath their surfaces. Enceladus has an ice crust that's several kilometers thick, but underneath its icy crust, it hosts a liquid, salty subsurface ocean, which also has a rich inventory of chemical organics. And the interesting thing about Enceladus is that it shoots out plumes on the South Pole, where these plumes are of course supplied by the subsurface ocean, and is shooting out these plumes in space, which the Cassini spacecraft sampled in 2008, which is exactly how we have this data of what's present in these plumes, giving us an insight of what might be present in the subsurface ocean. In addition, Titan is also a very interesting place because we have directly identified hydrogen cyanide in Titan's atmosphere, and it's also the only other place in our solar system that has a nitrogen-dominant atmosphere with traces of methane present in it, along with stable hydrocarbon liquid lakes, which are composed of methane and ethane, just for information. But the reason why that's so interesting is because it introduces a completely new world of aqueous chemistry where water is not the only solvent anymore, and we also have liquid methane and ethane to worry about, which is something that we just have not explored as much in the past at all. Both places, Titan and Enceladus, have unique environmental conditions, and with the presence of hydrogen cyanide and other complex organic molecules, we can definitely see the potential for chemical reactions leading to the emergence of life, similar to what we saw on the early Earth. Putting everything together, this study is an essential step in understanding the production of hydrogen cyanide in the atmosphere and its potential delivery to the surface, where it acted as a precursor to form biomolecules that life uses on Earth today, which not only enhances our understanding of the emergence of life on the early Earth, but it gives us these models of how we can apply this understanding to other worlds like Enceladus and Titan to look for life outside of Earth. The lead author on this paper is Dr. Ben Pierce, who is currently a postdoc fellow at Johns Hopkins University and is going to become an assistant professor at Purdue University starting fall of 2024. And I didn't realize it until recently, but I've actually been reading his work for quite some time because I was going through some of my old presentations and I found some papers that I analyzed for my higher level chem courses in college, and both two of the presentations that I saw were his papers. And I recently got the chance to meet him virtually, and he's just such an authentic person. He's so down to earth, and yeah, you should definitely go check out his paper, read his other work as well. It's super interesting. And if you made it this far into the video, I appreciate you so much, and thank you for tuning in. Like the video if you learned something new, comment down any questions that you have, and subscribe if you're new to the channel. I will see you all in the next one.